Paula. Good afternoon. We will start this paper session, which is the remote paper session number 4. We have 3 presentations of 20 minutes each one. The first presentation is entitled Self-explanatory error checking capability for classifier-based decision support system, and it will be presented by Silva Oliveira. Please, you have 15 minutes for oral presentation and then 5 minutes for questions.
Okay, thank you so much. Good afternoon, everyone. My name is Silva Oliveira. I will present the work I did with Professor Fernando Buarque, which is entitled Self-explanatory error checking capability for classifier-based decision support systems. I would like to start my talk. I'm having a minor glitch here with my presentation. Okay, now it changes. Information systems have been increasingly using opaque machine learning models, which means that being opaque, they don't make easy to understand how their inputs are mapped to the outputs. And for high impact decision scenarios, this is really a challenge, because when human lives or large financial sums are at stake, model explanations are highly in demand. This is a growing concern. It's in fact have been this way for a long time, but now countries which are really needing this kind of technologies have even started to make regulations, laws, and the area of explainable artificial intelligence is have been right for the last years. So in most cases, even when explanations are available, it is still up to the human to inspect this explanation to understand if these inferences are reliable or not. And there are at least 2 main problems with this kind of approach. First, not all decision makers have the same level of expertise, so that this poses a threat to decision support effectiveness. For example, a decision maker will have a low level of expertise, maybe starting his career, maybe you have a hard time reading the explanation texts or even interpreting the graphs and having the feeling if a given inference is appropriate or not. So a second problem is that forcing the decision maker to make this coherence check might exacerbate their cognitive fatigue. A medic, a high-level investment manager has really high mental demanding tasks, and forcing him or her to perform this check can also aggravate this problem. And there are studies that show that tired users tend to make worse decisions, and also they will tend to be less sensitive to identifying these coherence problems. So in this work, we propose an approach to imbue these classifier-based decision support systems with the capability of self-detecting inference errors and also explaining the perceived errors. Our hypothesis is that aiding the decision maker in perceiving these problems may ease their lives and might facilitate the selection of inference alternatives with higher probability of being correct. Our overview of approach is presented here in this figure. We consider that decision support systems possess a model database where different kinds of intelligent models will be stored. The process starts selecting one of these classifiers and performing an inference. After that, if the model is not transparent, and most of them really are not, the explanation generators will come in place to generate post hoc explanations for the inference. After that, the inference and explanations will be subject to what we call an error checker, which is a device, or for the scope of this work, a classifier, which will check if the inference probably is an error or not. When an error is detected by the error checker, the error explanation will be sent to the decision maker to inspect, and if he or she accepts the solution, the cycle finishes. Otherwise, a new cycle will start, probably selecting another inference method. And what about this idea of considering inference explanations as possible error evidences? Here in the left part of the slide, I put some questions which are common in decision support systems which are aided by explainable AI. For example, which attributes were evaluated as important class discriminators using for this specific inference or for this classifier? And we considered that if we could, by some means, quantify this explanation, I mean, the answer for this question, we could use them to train another classifier, a secondary one, to identify the errors performed during classification. So we start with a problem data set, for example, any data set used for classification, for example, the iris data set. After that, we submit these attributes and, of course, the patterns for decision models, and the inference will be checked to form these tuples here. And what is supposed to be put in these tuples? The value of the explanatory metrics, for example, the answer for some of these questions which are, of course, relevant to a specific problem, and all these metrics will be considered, of course, independent variables, and the dependent variable will be if this inference was an error or not. All these samples collected here will form what we call the error checker data set. And this error checker data set will be used to train our error checker classifier. It's worth mentioning that the more accurate a classifier is, the more imbalanced this error checker data set tends to be. This is why we put this class imbalance technique here. It can be subject to each problem, of course, but the point is, when a classifier is highly accurate, and we in most cases want this error checker data set will have more samples of the correct classification than of the incorrect classification. So for that, the need for this class imbalance part here. After that, the classifier will be trained and evaluated, and after will be subject to error explanations. These explanations, of course, will be put to the decision maker evaluation. I have one example of this later in the presentation, and I have also results about using a simple auto-fix routine to use this error checker verification. Now for the results, our study data sets were, as a preliminary study, these four. All of them are classification data sets, and they are available in the UCI machine learning repository. Each one of these data sets have different number of samples, different number of attributes, and also different number of classes. And what we did with these data sets, for each data set, we generated a small decision model database. For each data set, we trained instances of logistic regression, KNN, decision trees, artificial neural networks, and SVMs. And a starting result to show now is that we will show here in this table the results for the best and the second best models for each of these data sets. We can see here that the kind of model changed among all of them, okay, no problem. And we had somewhat consistent results among these different sets. And there's a point here which is important to highlight. Training accuracy and test accuracy were calculated using 60% of the data and 20% of the training data, I mean, the whole data set. And the simulation accuracy was calculated over the remaining 20%, which was used in the results that I will show you in the next slides, which refer to the checking of the error checker classifier. For the error checker classifier, and by this I mean by forming our error checker data set, we used these three explanatory metrics here. The first of them, similar accuracy, which accounts for how good a classifier is with training or test data, which is similar to the pattern I'm evaluating in the moment. Second, same class distance, where we try to check how close the current classification is of members of the same class, which are of course known in the training or test data set, and the other class distance, which is the opposite. Just to highlight what I mean with these two last ones is the following. Imagine that we had a classification and the patient, which is in front of me right now, was classified as a sick patient. What this measure here will tell is how close the data of the input data of this patient, which I classified, the model classified as sick, is close to other historical data considered as sick. And this other one considers the opposite, how far he is from the closest pattern, which is part of other class. So after compiling all these metrics for the previously announced data set, we made the compilation of training accuracy and test accuracy over the error checker data set. And we got these results. The best models were used as error checker for the next part of the experiments. And the results were, again, in some cases, I believe they could improve a little bit, but they were somewhat consistent for this time of our research. And after that, what we perceived was this. For this first graph here, we show in the blue bars the total number of simulation cases evaluated. In the orange, the number of errors which were performed by that top best classifier. In gray, the number of detected errors by the error checker, and in the last bar here, the yellow one, the number of fixed classifications by employing the second best classifier. And I would like to highlight that this was our initial idea of auto-fix routine, given at least two of the best models contained in our model data set. When the first one was considered failing by the error checker, the second one was used. And here we can see that this approach resulted in somewhat good results for the South German credit. Of 200 cases, 59 errors, 47 were detected by the error checker classifier, and 20 were fixed by the second classifier. This wasn't so good, for example, here in the heart data set, with 59 simulator examples, 15 errors, 11 errors detected by the error checker classifier, and only one correction. And here in the right part, I have results for the improvements in accuracy first, for the data using only the best classifier. Second, using our approach when detecting an error, check using a secondary classifier. And in some cases, we had some improvements in accuracy, sometimes 5 or 10 or even 20%. In other cases, really small improvements. And in the gray bars here, they present the impact of in accuracy, in gains of accuracy, if we could have fixed all the detected errors. And these values are really interesting and suggested to us that the error checker approach for these studied data sets could be promising. This is an example in graphical form, of course, of one single inference using our approach. For example, one instance was subject to a given classifier, was classified as class 0, let's suppose sick patient, and all these explanatory metrics were calculated here in the first part. In the second part, this evaluation of patient sick with this explanatory metrics were subject to the error checker, and an error was detected. After that, I used LIME, a common, at this moment, common technique for post hoc explanation extraction, and we got this graph here showing that with 97% of probability, this was really an error, and the most important characteristic for that was the similar accuracy. And down here, we have a textual error explanation, because some users, they prefer graphical, other textual explanations. And this would be the the translation of this graph. This sample was incorrectly classified with 97% probability because the classifier incorrectly classified 5 most similar samples. This example, of course, is an example which is somewhat simple. Probably a decision maker which wasn't so tired would perceive that this variable is 0. This would suggest an unreliable inference. However, if we consider that in other scenarios we might have a large number of explanations to be inspected, this approach could be aided a lot because we probably would change any, a reasonably large number of explanations for only one. Oh, finally, this work I just presented proposed the inference explanations to be used as means to identify and explain the accuracy of errors. These preliminary results encourage further studies, and the high point I would say is that even using just 3 explanatory metrics, we could detect most of the classification errors, at least for this data sets and for this specific experiments. And finally, the future errors. In order to make this approach more robust, we intend to evaluate a larger number of data sets, employ data sets which are more complex, also to use as decision models, classifiers which are more powerful, and finally, to develop a set of extra explanatory metrics which can be used for harder problems and also to deliver this to the community. So thank you so much for your time. Now I return the word for the chair.
Well, thank you, Flavio, for your presentation. So, there are any questions here in the room? Is there a possibility to make questions in the to make remote questions? Okay. So Flavio, I have a question related to the last point of your future work. As I understand, you have used some benchmark datasets in your computational experiments. Okay. So I wonder if you plan to use some new datasets related to your local data, for example, some problem related to data from Brazil, or with a real decision maker, or a real problem that you might face in Brazil?
Yes, I intend to evolve this initial study because, in fact, this is part of my PhD thesis. Among a larger contribution, there is a module there which is, we called it as an automatic evaluator of decisions, which will reside inside of a larger framework. And we really are interested in putting these things to work to evaluate, maybe with real users, how good this is. But even if we cannot make these experiments with real users, we need to evolve these experiments to use real world data. And we have down the road probably at least 3 opportunities to do this.
Okay. Okay. Thank you very much. Well, so thank you, Flavio, for your presentation.
Thanks as well.
So,
Hello. Okay, I'm the next. May I turn on my camera?
well, we will move to the next presentation. The next presentation is, the title is Passive Sonar Classification Using Time Domain Information and Recurrent Neural Networks. And the speaker is Nathanael Júnior.
Yeah, that's it. Thank you very much. My name is Nathanael. I'm here on behalf of Marlon, Souza, and José Manuel de Seixas. Marlon had some personal problems and he cannot be here to present it. I think you can hear me well, okay? So, we both, three of us are, belongs to Federal University of Rio de Janeiro, and the work is Passive Sonar System Classification using Time Domain Information and Recurrent Neural Networks. So, here is a summary of a presentation that we planning to finish on this section. So we have briefly introduced the problem that we have. We briefly also introduced the passive sonar systems. We present the method that we intend to get our results. In the method, we present recurrent neural networks in the most useful way that we find in the literature analysis as LSTM, long short-term memory models. Sorry. We presented also some figures of merit that we use to evaluate our systems, and we also present the cross-validation method that we use. Sorry. Okay. So, and after that, we presented the results and discussions and the conclusions and future works. So, first of all, Brazil, as you know, Brazil is a country that has the most part of his. Sorry, I had some noise here. So, I got some noise here. Sorry. Okay. Let's go. So in Brazil, have as we call is Blue Amazon. That is a region, is an economic region that we can exploit the economy and the natural resources that we have there. So the pre-salt, it's announced in 2014, has 80% of the oil, Brazilian oil, and 75% of the natural gas. So to protect this huge amount of resources, the Brazilian government implemented the ProSub program, that is a submarine development program. So in the naval environment, we have a large number of vessels, and with this, we need to the Brazilian Navy understand that we need some automatical decision system to help the Brazilian officers to understand if they are in threat or not. So the purpose of this work is inside of this environment. We propose to develop a passive sonar system classifier based on deep neural networks, in more specific sense, LSTM, and use a different signal processing chain, both in frequency and time, to see if we have some better results. Okay. So, as you know, passive sonar systems is a subset of this whole world that is a sonar system, but in the specific sense that we have here, the sonar can be classified in two ways: the active sonar systems and passive sonar systems. Active sonar systems emits specific sets of pulses and try to analyze the response of a given target. So we can, as you can see, for a submarine, for a military submarine, this is not a good way to go, because it's a little bit disturbing to send a pulse and send a signal that, okay, we are here. So we are not intending to this, because we need to be stealth, as stealth as you can. But we also have this passive sonar system that is only listen the signals in the marine and see if you can process the signals and understand if you can, first of all, tracking the target. After that, classify this target, and after that, make a decision. Okay. So we have different applications of these passive sonar systems. We have applications that detect of faults in pipelines, ecobathymetry, port surveillance, and guidance for submarines and other vessels that are in the sea. We have also these fish finders that we have for civilian applications, but we also have military applications that is very important for this. So this technology is very, very hugely applied. So the underwater environment is highly noisy. So we, in practice, we are trying to separate noise from noise. So the signal of interest is a vessel noise, and we're trying to distinguish of noising or background noise that you have. So as you can see here, we have this huge amount of frequency stacked. So the human shipping is in this range, so we have a huge amount of frequencies that are not interesting, so they call it background noise. So what is the passive sonar system do to analyze the signal? So first of all, we have these hydrophones here that is or sensors, and these hydrophones are applied for a beamformer. This beamformer gives some signals to time marking and frequency marking, and after that we have this detection, tracking, and classification. So in parallel of this main processing chain that we have here, we have also the LOFAR and demo analysis that gives some signal for automatic classification process. We can also apply here the temporal analysis that is a proposal of our work, and we are also can analyze the sound itself, the raw sound, and applied manual classification without any problem. And after that, we can add these 3 ways of classification and take a decision, or probably we can remove one of them and we can take a decision by itself. No problem at all. Okay, so what is this demo and LOFAR analysis that I presented in the previous slides? Demo is analysis that try to estimate some information about a given target that we are listening. So this analysis is trying to estimate the number of speed that we have in the ship, and LOFAR analysis is a more broadband analysis that trying to estimate some characteristics, noises, tones that we have on these ships. So I will deep dive on LOFAR analysis, so probably we should take care of a little bit more about it. So we take this bearing that was processed by the beamform. We apply a decimation. Here I put it here omega, capsulized omega, to apply a decimation that it's trying to squeeze the frequency range that we have. After that, we applying a raining window, a short time Fourier transformer. We apply some modulus function, and after that we apply this 2-pass split window that is a way to estimate the background noise and remove it from the signal. Because this is a common sense in Brazilian Navy, a way to process the signal coming from the sea, and this is a good way to do it, and we can extract some features that is very relevant to classification without any problem. So we are proposing here a temporal analysis that is a little bit different from LOFAR, because we remove some steps here. So first of all, we have this bearing, the same thing, in the same way, in the same sense that we have it before, but here we have this decimation process, a low pass band filter, and this low pass, it's trying to emulate the decimation, this honey window plus this short time Fourier transform, and after that we apply some normalization to present this event for the model that we have. So the response of a LOFAR analysis can be seen here in the left hand graphic that we have, but the response and the output of the temporal analysis that are implemented, as you can see, is in the right hand. So as you can see, we can also treat this signal as a time series. So that's the motivation to use LSTM model that can acquire very good results in time series modeling, as we know. Okay, so on this paper we propose two neural network models. The first one is MLP, that will be our baseline. And this MLP was trained with a set hyperparameter that I presented after this slide. And after that, we also proposed the recurrent neural networks, as no LSTM. And these two models was also applied to character recognition, or OCR, voice recognition, time series prediction. So these two models can be used as well for different applications without any problems. So what is the model that of a recurrent neural network that we use here? As I already said, long short-term memory, the LSTM, that is introduced auto loops to produce some paths where the gradient can flow, and this gradient will not explode or vanish through the time. So this model is very common have a lot of applications in the area. So in the or abstract, we presented a lot of references here that we can, as you can see, without any problem. But these LSTM neural networks have different gates that is very, very, very useful to train. So the forget gate, the input gate, and the output gate. Okay, I will not deep dive a lot because we have no time for this, but I'll explain everything here, and we can send this material to the audience without no problem. So classification process with many classes, as we have something around 20 classes, it's a little bit difficult to evaluate because accuracy, if you have a lot of classes, accuracy can go down. One of these given classes can go down and accuracy will not sense because there is not sensitive when we have a lot of classes. So we tried to evaluate this model behavior with a different sensor here. So we implemented this SP index that is geometric mean put it together with arithmetic mean. So here we have this. Here we have the accuracy as itself, but we also implemented the geometric mean of the efficiency, squared root of this. So as you can see, we are a little bit more sensitive to a crash of one class is in a specific way. So that's the point. We're trying to implement this, and this is a little bit more sensitive as once we compare with the accuracy. So we also implemented the cross-validation method to estimate the statistical uncertainty of our modeling applying. So we implemented here the K folds, with 5 folds to understand if you can understand the statistical uncertainty and trying to estimate it. Okay, so this is the training setup that we used for MLP. We use one hidden layer, neurons ranging from 10 to 100. That is okay because we didn't have a lot of events to estimate the hyperparameters of these models. And for LSTM, we use the number of cells coming from 25 until 100. We use supervised training. Our loss functions was coarse entropy. Our activation function was ReLU, and we normalized our inputs to zero mean and unity variance. The optimizer was the add-on optimizer implemented with TensorFlow, and the learning ratio was 0.001, 200 epochs, and the softmax was used as output. Okay. Our data set presented to us the Brazilian Navy. The most part of this data is Brazilian Navy recorded. That was recorded in the Guanabara Bay here in Rio de Janeiro. The resolution used was 8 bits, and the sampling rate varies for each class because different platforms was used to record the data that was presented here. So we have among our data 24 classes of ships, of vessels that was recorded, and the most part of these records are civilian vessels that was trafficking in the Guanabara Bay in Rio. Okay. So a computer of classifier was arranged in this hierarchical manner. So we use this super classes label to understand to compress these 24 classes in four huge classes that we use here to classification purpose, but we are not able to give to you the information of these classes because we have a huge confidentiality pointed here because it is classified data from Brazilian Navy and so on. We shouldn't not even give some label of this. Okay, so our data set comprises 2040 classes, sorry, and each classes has this amount of sorry, can you hear me? I got some.
Excuse me, Nathan, you already used 15 minutes, so we have 5 last minutes. Okay.
Okay.
Including questions.
Okay. Thank you very much. So we have this we have this amount of events per class, and we get this SP index values 76.3%. With an uncertainty of 2 and 72.7%. So the MLP was beaten by the LSTM. So we have this different amount of SP index that is very good. And we also have here this confusion matrix. Each model that we trained have the main diagonal in the good way to go. I will not spend much time here because we also spend some time, sorry. And the time domain MLP model was lower performed. That it's pretty understandable because we have a lot of noise here. But the time domain LSTM outperformed all the other models. That is very good. We have some comparison here with MLP model that was presented before by Golds that to get something around 70%. That's very good. So, but we have also some plans to apply these proposed methods for another levels of the hierarchy classification process, and we are also trying to implement this LSTM network in low-fire analysis that data that would be better than MLP and better than LSTM in the time analysis. So thank you for your attention. Sorry for the delay, and I pass the word for the convener.
Okay, thank you for your presentation.
Thank you.
So, is there any question? Okay, so I have one question. I wonder if this is a new problem, or I don't know if you have mentioned any previous work or the state of the art. What is known about the study of this problem in the literature?
Okay, so actually this is not a new problem. This is quite a classical problem for electrical Brazilian engineers. But with this data set, we have a huge word of challenges because this data set is comprised to 24 classes of vessels. So it's totally different from that the previous data set that we work on. Okay.
It's not a new problem, but the particular data that you have used is somehow a novelty in the study of this problem.
That's it. That's it.
Okay, so thank you again for your presentation.
Thank you for your attention, and thank you for the questions.
We move to the next presentation. I think we have another presentation on sonar systems. The title is Clustering and Bagging-Based Ensemble for Novelty Detection in Passive Sonar Systems, and the presentation, the speaker is Eduardo Honorato. Is Eduardo there? Trying to connect.
Hello. Can you listen to me?
Okay. So we see the top of your face, the upper part.
Oh, okay. Right.
Now it's okay. Thank you. Please proceed with your presentation.
Yes. Hello, I'm Honorato, and today I present the work entitled Clustering and Bagging-Based Ensemble for Noise Detection in Passive Sonar Systems. The topics of the presentation will be as follows. The passive sonar problems, where the importance of tracing the problem will be addressed. Novelty detection, where the model of novelty detection architectures will be discussed. Practical issues in novelty detections, where some practical aspects for deploying novelty detection systems and machine learning algorithms will be detailed. Developing evaluation, where the database uses the methodology and figures to match represented, experimental results, and finally the conclusions. Passive sonar systems are critical instruments for submarine patrolling. These systems are composed by arrays of hydrophones responsible for capturing the vibrations emitted by all the vessels, which in letter jargons are known as contacts. The contact noise often includes relevant information such as the vessel acoustic signature. The sonar operators are specific crew members trained to analyze the signals and identify if they correspond to a sonar previous nose signature. In other words, if a particular contact represents a possible threat. Automatic contact classification systems may be a valuable tool for some operators, since they turn such tasks more manageable, improving the decision-making efficiency and reducing the rated workload. To deploy efficient automatic contact classification systems, ideally, such process must consider database with most, if not all, existing vessels. Naturally, this cannot be realized, as many military vessels employ furtive strategies, and are kept secret. Bear this in mind, the existence of mechanisms capable of recognizing new classes of vessels is fundamental, since most automatic contact classification systems will be only capable of distinguishing between a limited number of vessels of ships in practice. In this work, novelty detection will refer to the act of identifying whether a given contact signals belong to a set of classes exploited for developing a automatic contact classification system, referred here as null classes, or another class generally named as null class. Typically, a novelty detector system is composed of two blocks: novelty score generator and decision maker. The novelty score generator has a role to generate a real score score, responsible for quantifying the level of similarity between some data on the analysis in the set of unknown instances, which can be implemented by a range of machine learning techniques. The decision maker is based on a user-defined real score decision threshold, to which the value of the novelty score is compared with, such that if the score is greater than the decision threshold, the system modification of value occurrence, otherwise a non-novelty. Novelty detection system may benefit from an ensemble of one-class classifiers, exploiting the power of multiple classified models, each one strictly developed to recognize to one class of specification and refuse the others. Previous works considered the ensemble of class specified models, treated by high accurate classifier, known as the hierarchical architecture. Thus, at first, a classifier module has the task of selecting the most likely class with the contact with the evaluation. Then, at second level, the class specialized novelty score generator uses a dictionary measure, used by the decision maker to define whether such signal represents a novel or not. A similar approach, the clustering-based ensemble architecture, has been proposed and adapted to our problem. The clustering ensemble architecture comprises cluster selector modules in opposition to the classifier model adopting the hierarchical architecture. Thus, instead of partitioning the data space into individual classes, a set of clusters may lead to a more refined class partitioning. We are proposing the cluster embedding-based ensemble architecture for novelty detection. Similar to the cluster ensemble architecture, there is also a cluster module responsible for assigning a cluster for some contact signal. However, cluster embedding ensemble essentially differs from cluster ensemble by adding a second-level processing represented by ensemble of multiple bootstrap clusters specialized in novelty detectors. These novelty detectors are generated over some bootstrap sample having an arbitrary size. Following a sampling with a replacement approach, produces to each cluster considering the training set partition between the same clusters. Finally, the final prediction variable is defined by the integration of multiple models outcomes, generating a specific cluster decision block output. In this work, we assume that the cluster selector model implemented with the k-means algorithm in both clustering ensemble and clustering embedding ensemble architectures. This simple fact unsupervised non-deterministic interactive methods split data into a specific number of clusters, being the number of clusters a hyperparameter. As in previous works, we investigated three instance-based machine learning techniques to generate a novelty score, namely k-nearest neighbors, the KNN, local outlier factor, the LOF, and the nearest neighbor density, the NND. Roughly, the role of these techniques are measuring the level of similarity between a given contact signal and the instance that integrates the clusters. The KNN considers the median of the distance between the data on the analysis and the instance belonging to its k-nearest neighbors, being the key a hyperparameter for the model. The LOF is based on the comparison between the local density of the data on the analysis with the local density of the instance integrated its k-nearest neighbors. Thus, these novelty scores define as the ratio between the average value of the reachability density of these k-nearest neighbors and the local reachability density of the data on the analysis. The NND is according to its most traditional formulation. This novelty score is defined as the ratio between the distance from the data on the analysis to its nearest neighbors and the distance between this data nearest to its nearest neighbors. And this technique does no hyperparameters to tune. The decision block present in each cluster from the cluster embedding ensemble architecture has a task of transforming a set of variable or set of novelty score into a single decision variable to define the system output. We indicated three approaches to accomplish this task: the merger, majority, and unanimous. The merger assumes an arbitrary function responsible for combining the novelty score from multiple models from a single cluster into a single variable. We consider 6 different factors: average, maximum, median, minimum, 25 and 25th and 75th percentile. In the majority, each novelty score is the specific decision maker block producing a set of individual decision variable weight bootstrap models. Then, it's innovative if more than half of the text points to novelty. In the unanimous, the decision variables are computed similar to the majority approach. Then, a logical AND gate is considered over all individual model decision. Thus, obtain novelty only if all individual models point to novelty. Some index are represented by the average no class detection rate and the average no class detection rate and the area of the detector operation curve. We must stress that the decision threshold defined for each novelty detector directly reflects on the average no rate and the average no rate index. To simplify, if the operator accepts the with a higher false alarm rate regarding identifying novelties in some emergency scenario, The system can achieve a higher null rate and a lower null rate. In this way, the relation between both performance index may be experimentally inferred by varying the threshold value to produce a plot named detector pressure curve. A quantitative measure of the detection pressure curve, the area under the curve, the AUC. To inquire a quantitative assess the performance of novelty detection systems, one would dispose of a set of null classes and set of null detection classes to emulate the existence of both sets. We split the available dataset into two groups. One of the classes dedicated to the system developed, the assumers do null, while the remainder treated as novelties. To define which class would integrate each set, an experiment was carried out, with simple novelty detectors based on the nearest neighbors being available a possible combination of null and null classes. The scenario with the lowest LC value was selected as theoretically related to the most difficulty novelty detection settings. The private database exploiting experiment was provided by Brazilian Navy Research Institute. It's comprised of acoustic index obtained from 263 runs of 28 ships belonging to 8 different classes, typically denoted by data from 8 due to security reasons. The acoustic signals is pre-processed with the signal per-passing chain. Here, at the end of the chain, the 557 from 2048 available FFT values are selected, covering the range from frequency from 0 to 3 kHz, relevant to the classic discrimination. This work will focus on the scenario represented by 5 null classes, A, B, C, F, G, and 3 null classes, D, E, H. Model assessments consider the tenfold resampling techniques. As a result, the dataset was split into tenfold, with 3 trios of training, the testing, and validation. The novelty detections were coded in Python using scikit-learn, NumPy, and SciPy libraries. In the cluster bang ensemble, we generated the bootstrap sample. We considered sample size equal to random selected percentage between 45% and 85% of the original sample size for each class. We assumed the hierarchical architecture as a baseline of comparisons, considering these better performance in reporting previous works. The first experiment validated the hierarchical and clustering ensemble architectures. The figure depicts the median of values for 3 instance-based novelty detectors, and it creates a number of clusters in the case of the clustering ensemble. Regarding the number of clusters, an increase of this value eventually results in a growth of the clustering ensemble detector performance, which is subsequently followed by a stagnation of performance or decrease related to over-specialization as expected. The results led to us to set the number of clusters in subsequent experiments as 11 clusters for KNN and LOF, and 13 clusters for NND. Most clusters in clustering banging ensemble experiments to perform hierarchical clustering ensemble counterparts. Again, the key NN exhibits the highest LC median values with the most configuration defined by the 25 detectors and decision block for the mean function. For LOF, the 10 detectors and decision block anonymous. For NNG, 50 detectors and the decision block with average function. To assess if the difference between the methods' performance are statistically significant, prefer to use the Friedman test with 2 confidence levels, 0.05 and 0.1 for overall performance evaluation. In the sequence, we adopted the NME test to identify between each parts of comparison. This difference may be observed only considering the cases to which the first test was positive. In other words, when the corresponding p-value is lower than alpha. Compare each novelty detection individually. The KNN cluster in bag ensemble to perform the KNN hierarchical and cluster ensemble being the later one, only considering the less restrictive scenario if alpha equals 0.1. the gain of clustering back ensemble over the hierarchical in the median C is about 1.8%, which is relevant for the safe critical problem in practical terms. For LoF, clustering back ensemble clearly outperformed the hierarchical in the clustering ensemble architectures, and have a gain performance of 3.3% in median C. For NND, the clustering back ensemble is also better than the other two, with a higher gain over the median C of approximately 4.4%. When including all models in this analysis, the KNN clustering bagging models related to the height of the median is statistically equivalent to the KNN clustering ensemble, the LoF clustering bagging ensemble, and the NN clustering bagging ensemble, still outperforming the KNN hierarchical, which is the current best approach reported in the literature to the database. An important point to stress about this finding is that the clustering bagging ensemble approach provides the performance of the less efficient Novelty detectors such that they could perform similar to the best model. Thus, clustering bagging ensemble may be a handy strategy to turn Novelty detector systems less dependent on the Novelty scores the detections adopted. The framework process is obtained interesting results, surprising the current best approach reported in the literature, allowing significant improvements over the detector performance, in some cases closer to 4.4% relative to the median C. We must highlight that such again is relevant for the application questions despite requiring the setting of highest number of the parameters in the design phase. In first words, we intend to combine these architectures with deep learning techniques such as the Golden Seamless neural networks, as well as consider this technique by over classes for specialized detectors, specialized Novelty detectors. And that is it. Thank you for your attention.
Okay, thank you, Eduardo, for the presentation. We have some questions for Eduardo.
Okay, thank you for your presentation. Regarding this last sentence in your slide, you are thinking in using deep learning to explore these specialized classes, the novelty detection. But the point is that for deep learning, it's not so easy to have these specialized machines to have a low margin or a strict margin for novelty detection. So, what's your strategy for this?
The classes specialized novelty detectors for deep learning techniques, especially for semi-neural networks, it require more data to train, but it's a more computational effort to train, but it can lead to better results because the non-linear approach, learning approach, can lead to more specific separation scenario of the null and null classes. So with the deep learning techniques, we maintain the same approach of specializing one class of this expertise for a single novelty detector, infusing all other classes of the systems or to train. In other words, we will be training a small scenario of only a few classes to recognize these classes, and infuse all other classes for non-specific detectors. So with this, we can detect novelty from any UNC detectors, any UNC classes.
Okay, so thank you, Eduardo. Thank again for your presentation. And we close this session, and now we switch immediately to the next session, which is the paper session remote number 5. The first work is entitled Machine Learning Approach for Trend Prediction to Improve Returns on Resilient Energy Market, And the speaker is Douglas Braz.
Hi everyone, can you see my screen?
Now, yes.
Okay, thank you.
Yes,
Thank you very
you can
much.
start your presentation.
I'm sorry?
You can start your presentation. Yes.
Okay,
Please.
okay, thank you. Thank you very much. Hi everyone, I am presenting our paper, which is the machine learning approach for trend predictions to improve returns on Brazilian energy market. This is a summary that I would like to present to you today so that I explain better our work and our main objectives, the material and the methods that we use it in the paper, also the results, and finally with some conclusions of our work. From the beginning, we have the energy market here in Brazil, which is an emerging market ruled by the Brazilian Energy Trading Counter, which is the BBCE, where companies can trade, can buy or sell energy. And with this market, this emerging market, we compare this behavior of this energy market as a financial stock market, so that we can try to predict the trends of the energy, and also to use these trend predictions as input to another framework that should be able to risk management and so on for companies that can buy or sell energy in this stock market, in this energy market, sorry. Buyers and sellers in this market, in this emerging market, can trade in different products, which is specific maturities, which is we can trade in a product that will be finished. We have the maturity in the next month, in the next 2 months, and so on. So this is why we are proposing a technique to modeling this price series as energy price series, so that we can apply our trend predictions and also to manage the risk of investment in this energy market. Another issue here that we have in this energy market is that transactions, we have a high financial value, so that we can extract some profit and earn some money, and also to risk management for these companies. So the main problems here is that in this market, in this energy market, we have a very low liquidity, because we have a low number of companies trading in this market. So we have a low number of buy and sell offers during a trade session. This increases the volatility of this market, even that it's a financial approach of the energy market. It's even with the emerging market, the volatility is very high, and also the oscillation is very high during specific periods, like when we have more rain or not, and so on. So basically, we want to create a trend prediction approach using machine learning models, so that we can create some financial strategies to buy and sell energy in this market automatically. So this is the main approach that we want to do. I bring here, and this is also a figure of our paper, that is showing the closing price of a conventional Southeast product that we have in this BBCE market. This is related to the energy here in Brazil. This is related to reais. And we have the prices ruled as megawatt hour. So basically, we have the same approach here in this energy market as we have in a financial stock market. So we want to bring that techniques that is used in that financial market, in many financial markets spreading around the globe, to this energy market, so that we can see if it is going up or if it's going down, so that we can create automatically strategies. The Brazilian energy market has it's totally dependent from the rain. So basically, every single I cannot say every single, but the main approach that try to predict the price of the Brazilian stock market, the Brazilian energy market, deals with the rain forecast. So it is going rain. Perhaps the price of the energy market goes down, and if it's the opposite, if we don't have the rain, perhaps the price of the energy should increase, because we need to turn on some thermoelectric power plants, and this increases the energy in the Brazilian energy market. So in this scenario, we want to provide a totally price serious approach that deals with the trend predictions in the energy market, using machine learning for that predictions, with the main object of increasing the financial returns and also managing the risks for energy companies, so that we can create, as I told you, some strategy, some automatic strategy to trade in this market. We have some materials and methods that we use in this paper. This is an initial paper with our project, and this initial paper, we modeling the price series as maturities. For instance, as I told you, we have the energy products in our energy market. So we have the maturity related to the monthly, quarterly, annually, and so on. So basically, we have many products, and we need to create a single time series so that we can use this time series as input to our machine learning models, so that we can also try to predict the trend of the energy market. So instead of using many products, we converted all these products in a single time series, which we named as maturity. So to do this, we model the product one related to the next month, the next maturity month, as a maturity M1. And for the next 2 months, the maturity M2, and for the next 3 months, the maturity M3. For instance, if we are at January from 2022, M1 refers to February, M2 refers to March, and M3 refers to April of 2022. So basically, we are looking to next month is related to M1, the next 2 months is related to M2, and the next 3 months is related to M3. So in this, keeping this in mind, we can create just one single series, so that we can deal with the series as a financial approach, as a time series approach, and then we can create our strategies to trade in this series. But basically, we are creating some just a single series from many products that we are dealing in this energy market. We have some problems, for instance, when we change the month. And when we change the month, perhaps the price can be have a difference between them, because we are trading in the product from the next month. Supposing that we are in January, the next month is February, and then when we change the month, perhaps we have this problem because the price is different from 2 products. But we are not dealing with this problem right now. But we have this problem in this approach that we are creating this price series. We are using daily closing price from each maturity for each price series that we have. The closing price is the last traded price during a trade session. We do this because we want to buy one day. We want to buy the energy in one day, and we want to sell it in another day. So we are using closing price so that we can trade at the end of the session. Low liquidity in this market, as we discussed, does not necessarily correspond to the price at the closing session. Perhaps we can have the last trade price during the trade session not close to the end of the trade session. So the last trade price could be, for instance, a price that is trading in the middle of the day. But for us, this is the last traded price, and we are working with this closing price. We are naming this closing price as the last trade price. The problem in this approach is a binary classification problem that we want to predict if the market is going up or is going down. The input to this binary classification problem is some meta features based on the price series that I will show you. And the output of this binary classification problem is the difference between the closing price from today and the closing price from tomorrow. So I have the difference between these two close prices. And if this difference is a positive, we have an uptrend. If this difference is a negative, equals 0 or negative, we have a downtrend in this case. So we have a binary classification problem. To deal with this, we created a supervised machine learning approach, which is used a machine learning model as a random forest. And we had also analysis of the financial return of the strategies that uses the output of this machine learning model as input for the decision. If the forecast, for instance, is an uptrend, then we can buy the energy. And if the forecast is a downtrend, then we can sell this energy product. To calculate the return is the same approach that we are using to calculate the trend. So we have the price from today, the price from tomorrow minus the price from today, for instance, so that we can trade. So this is the return, and we are using this return to calculate this return of the strategy, the financial return of the strategy. We used as input some basic features. We separated them as four groups, 4 sets. The first one is some basic metrics, which is the trade volume during a trade session, and the open, high, low, and close prices during a trade session. The open price is the first trade price during a trade session. The high is the highest price, the low is the lowest price, and the closing price is the last traded price during a trade session. We also calculate some technical analysis indicators. These technical analysis indicators is rarely used in financial scenarios, and we calculated 17 technical analysis indicators. I bring to you some examples of these technical analysis indicators. You can see the description and how can you calculate the technical analysis indicator in these papers that I'm putting this reference. We also calculate some lag features, which is the return price from the previous n days and the closing price also from n previous days. And also some sessional attributes, which we named as, for instance, the day of the week that we are trading, the day of the month numbers, and the month of the year, because we want to put some seasonal attribute in this machine learning approach, in this supervised machine learning approach. We also created a mixture of experts-based strategy, which is we created three experts The first one is an expert that is expert in trading up, trained in up sessions during a year, for instance. We have an expert in the down trends, and we have an expert which is balanced. We trained our machine learning to create experts in the uptrend, downtrend, and a balanced trend, which is the mean accuracy during a grid search, so that we can turn our hyperparameters from the machine learning approach. So basically, we have these three experts, and we aggregated them to produce a simple output of the machine learning, which is up or down. So we are looking to decision if the expert in down's decision say that the market is going down, then we return the downtrend output. If the decision of the expert in uptrend says that the market is going up, then we return the uptrend. If the decision of uptrend is saying that is up, and the decision of downtrend say that it's going down, then we return the balanced approach. So basically, we mix the expert based on combination of the outputs of these three experts that we have. The results
Douglas,
were calculated.
You already took 15 minutes, so you have 5 minutes, including the time for questions. Okay, 5 minutes.
Okay.
For your presentation.
Thank you very much. I just
Okay.
presenting. Okay. I'm just showing the results. We have the mixture of experts-based approach, which is the best one in terms of results, in terms of financial results. Even that these experts is not related to the best results related to classification results. Okay, I'm just presenting some financial returns related to the downtrend, the uptrend baseline algorithms that we created, the balanced output that is produced from the machine learning model, and also the mix of experts related to three maturities that we created some experiments. The proposed strategy improved the financial return. This is the first work that uses data from the Brazilian energy market for trend forecast. And also we have that limitation that we discussed, like a low liquidity in the energy market, so that we were analyzing another features to use as input to our machine learning models, like rain forecast flow of during a season. We also using complex network for selecting important stations in the Brazilian the Brazilian energy market, and also using BNNS simulation to calculate the spreads in the order book, so that we can use all of these features as input as well. Thank you very much. I'm open to some questions if you have. I'm sorry about the delay.
No, we are okay with time. Thank you, Douglas, for your presentation. Any question? Okay.
At the beginning of your presentation, you mentioned that for some days there is the need of storing energy in case bad weather or something like that. Did you find any correlation between the best time to sell energy being also the time you need to store most energy for the next month due to weather issues or something like
that? We conduct some experiments trying to see if that features that I told you, like the seasonal features, is a related feature, so that we can put the correlation between some periods during a year, for instance, with the output of the price and if the price going up or going down related to these features. And we did not see any correlation between these features. As I told you, this is an initial project, initial paper in this project, and we are just dealing with the price series. But right now, we created many features to use as input, like the flow, the rain forecast, and the rain forecast is the best one to use as input to the machine learning model. Not this price series, but this one related to the seasonal features, we did not see any correlations between to trade and also to stock some energy and sell energy with these features.
Thank you.
Is there any other question? You? No? Okay, so we thank again Douglas for his presentation.
Thank you.
We will move to the next presentation. It's entitled Hybrid Models Based on Error Correction to Predict Thermoelectric Power Plant Fuel Consumption. And the speaker is Elias Siqueira-Filho.
Hello.
Hello, Elias.
Can I share my screen? I cannot start sharing the screen while other participant is sharing.
You have to share your window.
Yes. Oh. Okay, just a minute. Sorry.
Okay.
Do you see the
we see all the PowerPoint. You have to select the.
Okay. Can you see the full window?
Yes, the full screen. Yes. You have 15 minutes for our presentation and then 5 for questions.
Okay. So, hello everyone. My name is Elias Amancio, and I'm from University of Pernambuco, Brazil, and Advanced Institute of Technology and Innovation. I will present the paper called Hybrid Models Based on Error Correction to Predict Thermoelectric Power Plant Fuel Consumption. So initially, it is important to say that the Brazilian hydrothermal system has been passing through several changes in recent years in order to minimize the total cost for the operating the system. In example, in addition to the new wave and decomp stochastic models that are already being used for time series forecasting, the same model was implemented to determine optimal levels of dispatch for the system, considering a very short term horizon. So the responsibility of each thermoelectric power plant to guarantee an optimal operation has become really challenging. And it's even more challenging for diesel and HFO thermoelectric power plants due to a high unit cost of electricity and because of the system that requires quick actions in case of an emergency situation. So one way that guarantee that the system is always available for this type of situation is through an engine maintenance planning. These maintenance planning are currently carried out based on technical know-how of the team, simplified analytical models that try to seek and describe mathematically the behavior of the engine, and also through continuous monitoring of the engine for real-time emergencies. So based on historical data and through continuous monitoring the system that already exists in many power plants, it's possible to use time series forecasting techniques, both linear and nonlinear, for a set of benefits. For example, system prognostic tasks, to better understand the power generation system, and also to serve as an auxiliary tool in the engine tuning process. So considering existing works in this area, there are several studies that use time series forecasting techniques, usually applied in fuel consumption, energy generation, and gas analysis predictions, usually in coal-fired and steam thermoelectric power plants. It's important to mention that there are a few studies in other applications related to small to large engines. However, we could observe that there are a few works that can explore the use of these techniques applied in large TPPs engines powered by diesel and HFO. Thus, this work aimed to apply autoregressive forecasting models to analyze the fuel consumption on a real engine used in a Brazilian power plant. So this work used historical data from Energética Suape 2 plant, power plant located here in Pernambuco, Brazil. Data collection was carried out from the monitoring system, and 23 variables related to energy generation and fuel consumption were selected during the period from May to December 2021. It is important to say that the data is collected in real time, 24/7, and it's stored every 7 to 10 seconds, depending on the variable, with a maximum limit of 1 year. Well, for data preparation, the first step was to process each one of the analyzed variables. In this step, all periods containing outliers, empty information were identified, and each of these samples was replaced by a linear interpolation between adjacent values. Also, to maintain uniformity in the model inputs, it was necessary to group the samples in equally spaced values of 1 minute. It's a requirement for time series forecasting. And after that, data normalization was performed on the values between 0 to 1. And finally, the data was divided into training, validation, and testing sets. For this work, the last engine operation was separated as a test set, while the rest of the data was applied to training and validation set. Correlation analysis. We performed a correlation analysis between each one of the variables to set which parameters should be used as input for the multivariate models to make the prediction process more effective. Initially, we used Pearson correlation matrix to select and ensure the variables with correlation higher or lower 0.7 and minus 0.7. In the end, to predict fuel consumption output, 8 variables were selected as input, as described in the presentation. The reason for selecting these features was to reduce the computational effort and speed up the process of training. Obviously, using the 23 variables would be a very complex process, and the gain will not be as relevant. And after dataset division, different linear and nonlinear univariate and multivariate models were individually adjusted and evaluated using neurometrics and visual response of the predictions. Briefly speaking here about the configuration of the analyzed models, we used Euler-Walker equations for the R to estimate the coefficients of the R, since this approach already guarantees optimized solution for the autoregressive models. ARIMA and multiple linear regression were used as a baseline for the other models. And for the models that used artificial neural networks, 3 scenarios were considered, where the first one is a univariate autoregressive neural network. The second one is a multivariate or autoregressive neural network. The third one was used on the residual errors predictions for a hybrid approach. In this research, the algorithm that selects the orders through the first PSO module, the blue one, and then estimates the coefficients on a second PSO module, the second one, the red one. with both using global topology for these tasks. And in the end, ARIMA PSO model with minimal root mean square error is selected, like the example shown in the right. And for the hybrid approach used in this work, it was first proposed by Zhang, and it's based on residual error correction. In this case, we selected the best linear model based on its performance and used the residual series as input to a multi-layer perceptron to predict the future values of the residuals. And in the end, the result was the sum of the linear model forecast and the residual model forecast, which can greatly decrease the associated error and capture nonlinear patterns that the base model couldn't observe. Our parameter adjustment. It was observed that the analyzed time series was not stationary according to the autocorrelation function in ADF test analysis. So it was first differentiated. 10 orders were analyzed to define the best model arrangement. And from this analysis, order 3 was chosen because there was no significant improvement with higher orders. The ARIMA estimated by PSO modules determine autoregressive and moving averages orders as 1. The first module converged with only 6 iterations, while the estimation of the coefficients took much longer to converge, as you can see in the right figure, being able to stabilize around 150, 170 iterations. This can be explained due to the complexity involving on steaming the right coefficients on a continuous space. Through the MLP training, it was possible to see that the use of neural networks individually to perform predictions, univariate case, needs to capture linear and nonlinear patterns. But in this kind of time series, there is a predominance of linear patterns, so the training process is simpler. But in the other hand, in the hybrid model, the neural network is only used to predict errors that, by definition, not have clear patterns, so it makes the convergency and the training process more difficult, as you can see in the figure in the right. Regarding statistical analysis, we simulated the nonlinear models 30 times in the validation set to analyze whether or not there was a statistically significant difference between the neural network models. Visually speaking, in the graph, it's clear that the multivariate MLP model responded worse than the univariate MLP model. But the two hybrid approaches were very similar to each other. So first, we used Friedman tests to verify if machine models were behaved different or if their response was statistically the same, which confirmed that they were different. And two sample Kolmogorov-Smirnov tests confirmed that the hybrid models are equal. Performance evaluation. Considering only the linear prediction models, R3 obtained the best combination of error metrics, but the use of the PSO to estimation and identification reduced both error metrics by 2 and 5%. But talking about the nonlinear techniques, the univariate MLP was more capable of describing patterns individually than the linear models. And the addition of new inputs in the MLP affected the ability to follow the series variations, causing an increase in the mean absolute error. And finally, the hybrid approach models had the best combination of error metrics, as highlighted in the table, being superior to any other tested model. But talking about the performance of each model on different stages of the engine operation, it's possible to visualize that each model behaves different depending on the situation. It's hard to see on the screen, but all the models were able to follow the system startup just fine. However, it's possible to achieve a prediction much closer to reality when nonlinear prediction models are used: MLP, univariate, multivariate, and the hybrid approach. For shutdown stage, the models could follow the linear drop, but none of them reacted to a sudden change in fuel flow in the end of the shutdown, being the multiple linear regression the best for this task and the more stable model. For regular engine operation, the patterns observed by each model are different. The multiple linear regression presented the worst performance by any model. It's a yellow line, by always be keeping itself separate from the fuel consumption. And the hybrid approach is the pink line. It's the most sensitive by far among the models applied, making it capable of capturing disturbances in the system more quickly than any other model. And finally, one very important stage of operation is sudden drops on fuel consumption. It's clear that none of the models were able to predict this type of variations. However, in further studies, we were informed by the Thermoelectric technical team that these sudden drops can be explained by an interruption in the fuel intake valve. When the valve is closed, the fuel that had been lost through micro leaks is reused during this period. So it's basically an unpredictable situation for any model due to it's not read by the sensor that the model are trying to predict. So in conclusion, we can say that the linear and nonlinear autoregressive prediction models are an alternative to predict fuel consumption on a real thermoelectric power plant fueled by diesel and HFO. In summary, we could observe that the model performance depends on the engine operating stage, and the hybrid approach had the best overall performance. The error reduction achieved by the use of the residual correction was about 33% when compared with the best linear model. And this model was able to recognize operating disturbances. And finally, autoregressive prediction techniques can be potentially used as a tool on a real TPP engine to support maintenance activities. The authors want to thank Energetica Swap tool for supplying the underlying data, the Advanced Institute of Technology and Innovation, the CNPq and Araucaria Foundation for also support this research. And that's it. If you have any questions or comments, you're welcome.
Okay, thank you, Elias, for your presentation. So, you have any questions? No. No. I wonder regarding the previous work that you have mentioned in the state of the art. You mentioned that there are some related problems, but particularly the novelty of your work is the consideration of this way of generating the energy. Can you explain a little bit more the difference between your work and the previous work?
Yeah, of course. There are a lot of works that use time series forecasting techniques, mainly on coal-fired and steam thermoelectric power plants. It's a well-known kind of model applying in these situations. There are some works that use time series forecasting techniques on small engines, some of them vehicular, some of them maritime engines, both large or small engines. But there are few works that use time series forecasting techniques, mainly autoregressive models applied in big engines, motor generators, applied on a thermoelectric power plant. So the main goal of this this work was to try to use this kind of techniques applied on an engine and a system so big than the thermoelectric power plant.
Okay. Thank you, Elias. So thank you again for your presentation.
Okay.
And we move to the last presentation, which is entitled Reinforcement Learning Applied to the Routing and Spectrum Assignment in Elastic Optical Networks. The presentation will be given by Ivan Rios. Okay. Hello, Ivan. Are you there?
Good afternoon. You try to share the audio, please, of the video.
We are trying to show your face.
Good afternoon, everyone. I am Ivan Rios, and I want to present the work Reinforcement Learning Applied to the Routing and Spectrum Assignment in Elastic Optical Networks. We are from Facultad Politécnica, Universidad Nacional de Asunción, from Paraguay. The routing and spectrum assignment problem is considered a NP-hard problem. Given a request with a source node and destination node, it consists of routing and assigning the corresponding spectrum, complying with the following constraints: contiguity, continuity, and no overlapping of the spectrum assigned to the request. Reinforcement learning is a type of machine learning technique that enables an agent to learn in an interactive environment by trial and error using feedback from its own actions and experiences. We have three types of machine learning: supervised, unsupervised, and reinforcement. Supervised is task-driven, unsupervised is data-driven, and reinforcement is learned from mistakes. Though both supervised and reinforcement learning use mapping between input and output, unlike supervised learning where the feedback provided to the agent is correct set of actions for performing a task, reinforcement learning uses rewards and punishment as signals for positive and negative behavior. As compared to unsupervised learning, reinforcement learning is different in terms of goals. While the goal in unsupervised learning is to find similarities and differences between data points, in the case of reinforcement learning, the goal is to find a suitable action model that would maximize the total cumulative reward of the agent. The figure below illustrates the action-reward feedback loop of a generic RL model. Study approaches. In elastic optical networks, we have the RSA problem, and we choose the dynamic approach of RSA problem, and then we have studied classical heuristics versus Q-learning techniques. We present two approaches based on Q-learning aimed at solving the routing problem, named in this work as Q-learning routing softmax QRS and Q-learning routing epsilon QRE, using the exploration technique of softmax and epsilon greedy respectively. Thus, we also present two approaches based on Q-learning applied to the spectrum assignment problem named as Q-learning spectrum assignment softmax QSAS and Q-learning spectrum assignment epsilon QSAE, using the exploration technique of softmax and epsilon greedy respectively. Finally, we combine them for a complete solution RSA using Q-learning. As we mentioned earlier, these two techniques, epsilon greedy and softmax, are responsible for making decisions. The epsilon greedy uses a number epsilon between 0 and 1 as a scheme parameter to decide what action to take. And softmax, or Boltzmann, is a technique of softmax exploration that uses the Boltzmann distribution function to assign a probability to the actions to create a graduated function of estimated value. This is our general implementation scheme. Step 1, request arrive. Step 2, initialize data structures. Step 3, for each independent simulation. Step 4, for each request S. We have step 5, get route according to routing algorithm. Step 6, get frequency slots according to spectrum assignment algorithm. Step 7, insert into the network, and then update QR and QFS table, and then we finish the step 4. And then we calculate blocking probability, and then we finish the step 3. The results of the simulations of our algorithms were performed considering the NSFNet topology with 8 core nodes and 6 edge nodes. The simulations were performed on a computer with an Intel Core i7 processor, 8 GB of RAM, and a Windows 10 operating system. The Q-learning based RSA algorithms and simulations were performed using Python 2.7. The tests were performed simulating a dynamic load on the network where the number of requests was established considering the size of topology. The time of duration of the communication was randomly established with a uniform distribution for all scenarios with a minimum value equal to 5 units of time and a maximum value equal to value 15 time units. The spectrum load was established at 10 frequency slots in the homogeneous load, while for the heterogeneous load, random values uniformly distribute between 1 and 10 frequency slots were established. The optical links were set up to 16 frequency slots. Each result obtained in both sets was considered an average of 30 independent simulations of 1,000 episodes or time units each. For the configuration of the Q-learning algorithms, the learning rate values alpha and the discount factor gamma equal to 0.1 and 0.01 respectively. For the NSFNet topology, k equal to 3 was confirmed. The minimum number of requests per episode Smin was set up to 1, while the maximum Smax was 25. We compared the proposed QRS and QRE routing techniques in terms of blocking probability with the SP and KSP routing schemes. As we can see in figure, the routing based on the SP heuristic is the one that keeps the blocking probability value equal to 0 at low loads. The routing based on Q-learning, QRS, QRE begin presenting higher values for these loads with respect to the KSP heuristic. It presents the worst performance with blocking probability values higher than the competition in all loads. As we can see in the next figure, QSA is superior in performance to RF heuristic at all loads, low, medium, and high. However, QSAS ranks last. Additionally, we observe that FF heuristic is the one that achieves the best result in any load. As we can see in the next figure, the SPFF strategy is ahead, leaving QRE and QSAE and QRS, QSAS in the second and third place, respectively. As conclusion, we propose QRS and QRE for routing and QSAS and QSAE for spectrum assignment to minimize blocking probability. QRE and QSAE are based on epsilon greedy, while QRS and QSAS are based on softmax. The results show that the QRS and QRE algorithms are better at medium and high loads than the classic shortest path and k-shortest path heuristics in the routing problem. Considering the spectrum assignment problem, the first fit heuristic and QSAE obtain the best results. Consequently, we can mention that the algorithm QSAS is the one with the worst overall performance. Finally, we can conclude that the QRE QSAE algorithms for the joint resolution of the RSA problem is promising compared with the combination of the classic SPFF heuristics. The QRS QSAS combination presents the worst performance in all scenarios. Considering these results, we can conclude that when using Q-learning based epsilon greedy as a solution to both problems is promissory. From the conclusions, the authors propose to analyze other objective functions for the different algorithms with Q-learning proposed in ion networks, such as the execution time. Thank you so much for your attention.
Okay, thank you, Ivan. Is there any question for Ivan? Okay.
So thank you for your presentation. I was wondering, because you show some results when you compare your proposal, you use reinforcement learning for routing and for spectrum assignment, and sometimes your results are even worse than what I can define as the simplest way to solve this kind of problem using the shorted path and first fit. And what I was wondering is that when you use, for example, first fit, you have the very traditional problem that is to have all the requests being allocated in the same part of the spectrum. So what did you observe in your experiments that maybe can yield to have even worse results than the results for the shorter path and first fit approach?
Dan, you understand the question?
Sorry, I had a little problem of my internet. The last part I wasn't listening.
So
Only
what
last
kind
part,
of blocking did you observe in your network? Did you analyze?
Okay, I show the presentation.
The last question is, what is kind of blocking the formula? Is the right of the number of the request blocked over the total request that come to the network?
Sometimes you have the blocking because you don't have
can you
routes to attend to the requests. What kind of?
The blocking is the overall workload on the network. In each time, we contabilize what number of requests ingress in the network and what number is left in the network. This is the measure. The first question, why sometimes the heuristic algorithm is better of Q-learning is when we have a low load. With the network is low load, is better use the classical heuristic algorithm. But when the system is in a high load, is better use the intelligent algorithms.
For real situations, what the companies they expect to have is roughly something like 1% of blocking probability. So, because I have worked with some of the companies in this kind of scenario, and they just allow to have this kind of solution when you have something like a maximum of 1% of blocking probability. So, you're stating that in this case, heuristics are better than reinforcement learning. Okay.
Okay, so thank you for the question and for the answers. We thank Ivan again, and we close the presentation.
Thank you so much.
So this was the last presentation, so we close the session. Okay. Thank you for attending. Hope
Well, we are going to begin with the closing ceremony of the 8th IEEE LA-CCI. Well, the first, we would like to begin with the prize award ceremony. And we are going to give the winners of the thesis contest. On the master thesis category, there were there was only one finalist, and so he made his presentation yesterday. So the award goes to Diego Buenos Aires de Carvalho for his thesis Map View Exploring Datasets via Unsupervised View Recommendations from University of Pernambuco. Close. And here is one of his mentors, something. And then in the category of PhD thesis, we have 2 finalists. Both works were considered really strong works. Well, I should have begun saying who was the jury. I omit that. The jury was integrated by Ayala Rosa, Gonzalo Tejera, Carlos Coelho, Héctor Cancela, and Martín Pedemonte. And I was saying that in the second category, PhD thesis, the 2 works presented yesterday were very strong with many publications, many interesting points. But we have to give one winner. The jury decided that after evaluating all the aspects, the presentation, the publications, the innovative ideas presented, the winner is Marcelo Rodriguez de Holanda Maya for his work, Novel Data Mining Methods and Applications in Combinatorial Optimization and Bioinformatics from Universidade Federal Fluminense. We'll be sending then these certificates and also the certificates to Marcelo de Souza for being a finalist of this contest. Well, after the awards of the contest, I would like to say, well, thanks to the people that participate from these conferences. It was a bit difficult because maybe some of you don't know, but you will say, why somebody is organizing a conference when the World Cup has started? But the conference, the date of the conference was set before the World Cup was set in November. Originally, the World Cup was going to be on June or in July, and then they moved it, and so we have this problem. But we have many interesting work from Brazil, from Chile, from Colombia, so it was interesting to receive you in Uruguay. I would like to say some words thanking the chairs from the different tracks and also the local people that help us. That it was very important so we can develop the conference. I would like to start with our sponsors that help us to keep on with the budget. It's Intendencia de Montevideo, Ministerio de Industria, Energía y Minería, Ceibal, CLEI, ICT4B, UTE, Adhesiva, and Smart Lab. That's the last one. And also would like to mention the people from the local committee: Pedro Piñeiro, Lorena Echeverri, Libertad Tanzini, Ayala Rosa, Gonzalo Tejera, Antonio Mautone, Jimena Ferreira, and Gaston Note, and also to the people to help us with receiving you, trying that you pass well here, Eduardo and Monica, the people from OpenThing that when we say that we had to make this conference hybrid and have to transmit on the internet, they have many good ideas on how to do it. And so I would like to give an applause to Enrique Severo and Leandro Fernandez that help us with all of this. And finally, for my four members of my group that were there helping with all the process of filming and transmitting. That's Manuel Freire, Jimena Ferreira, Gonzalo Berger, y Raúl Marichal. Thank you. It wouldn't be possible without your help, so it's important for us. And so now we have finished with the conference here in Uruguay, and the next year will be received by the people in Brazil. We hope that we can be at the conference, so we can be in beaches like the one that we are going to show. I don't know.
Well, I have not much to say, just to thank you to everyone. It's not easy to organize a conference just after the pandemic. It's really complicated in the middle of the World Cup, but it was successful. We had, as the chair said, the program chair said, 62 submissions, which is okay, but we hope to put these numbers up. And Carmelo will talk about the next conference. But to me, I think the only thing that is really wise to do is to ask everybody to join me applauding the organizers, and you really deserve our thanks. Well, but we next year we are having the 10th year after the first idea of organizing this. Carmelo, who is the chair of the task force, will give you the details. Thank you.
Okay, thank you, Martin. Thank you, Hector. In your names, I would like to thank you, everybody who made the conference possible. I know that it's not easy to organize something in the middle of the World Cup after the pandemics. In fact, in Brazil, actually, we are having restrictions again because of the COVID. But I think we have to restart, and this is the point. I think we are trying to seek for the best mode to work. In this case, we had some presential presentations. We have some remote presentations. I think it was fine. Some people are watching on YouTube, and some of the people are watching the presentations after the presentations occur. So we have this new way to store the information about the conference, and I really appreciate your help on this. And what we intend is to have, the things ramping up in the next edition. So thanks a lot for your job. And as Fernando mentioned, we will have the next edition next year in Porto de Galinha. I don't know if you have but this is the photo of the beach. It was chosen 10 times in a row as the most beautiful beach of Brazil. So I hope you enjoy. We did the first, the 0 edition of LA-CCI 10 years ago, and the same place that will be held in the next year. So I hope you can make it to go, not to just make remote presentations, but to go to join us in Porto de Galinhas. It's quite near to Recife. We have a huge infrastructure to receive you all there. Okay, we have many tourism activities over there too. So it will be on the same time. I think is roughly in the 29th of October. I think is this. So end of October. So I hope you can join us. Okay. And again, I would like to thank you a lot for all the work, and thank all the task force members for supporting all the activities. Okay.
Thank you. It will be a pleasure to be in Porto Galinhas.